Hi everyone, thank you for attending my talk. Thanks Tony. My name is John and I'm a graduate student at the University of California, Berkeley, as Tony said, in the ME department. I work in the Model Predictive Control Lab, and my research focuses on control algorithms for automotive applications. So today I'm going to talk to you about Julia and self-driving cars, but of this size, so the smaller ones. I should acknowledge my colleague Tony here for initially pushing me to use Julia. It took a while to get this to work on ARM, but it's been a rewarding experience. So I'm going to go ahead and start off with a video just to show you a project that a colleague and I worked on last semester. And this demo actually uses Julia. Let me see. Sorry guys. I'll try to forward to where it left off. But it's just a slow motion of what had happened, so. It was a drift parking project, so pretty cool stuff. Okay, so we call this RC car the Berkeley Autonomous Race Car Project, or BARC for short. We began developing this platform about a year ago, primarily to design and test control algorithms. So at a high level, this system consists of an RC car, which you see here. It's a 1/10 scale model. And the additional onboard electronics consist of a suite of sensors and a microcontroller to sense and react to the environment. All our software builds on open source projects, tools, and libraries. And we try to keep this system relatively low cost, so it's about $500 altogether. So I'll just first give an overview of some of the main components. So first we have the microcontroller, which is an Odroid XU4. It's from Hardkernel, which is a Korean company. And if you're not familiar with it, you can think of it like a Raspberry Pi with just more power. It runs on ARM, runs Linux. You can see the specs there. We also have an Arduino, which acts as a hardware interface between the sensors and the Odroid. So this is mainly for the electrical connections to send and receive signals. We also have a inertial measurement unit. So this gives us information about the acceleration, angular velocity, and orientation of the sensor, which is fixed to the frame of the car. We also have encoders, which consist of a Hall effect sensor and magnetic pins along the rim of each of the wheels. So this basically gives us information about how fast each of the wheels is spinning, so we can detect if things like slip. We also have a camera and ultrasound sensors. So the camera is a 2-megapixel mono camera, which collects has 30 frames or more per second, depending on the resolution of the image, and has a sonar rangefinder, which provides a measurement of the distance between the sensor and the nearest solid object. So just to kind of show you what some of the data that's coming from the sensors, I set this up real quickly. Here we go. Here. So let me run this. Sorry, one second. So here I'll take the hood off, and you can see all the electronics inside. And what you're seeing here is basically a feed of this camera. I took off the mount here, and the resolution's a little poor right now. There's a little bit of latency because I'm not doing any compression. But you see a camera here, and then on the left there you see, or your right, you see a plot of the IMU data. So really all these sensors provide a wealth of information about the environment. And we use this information to control the vehicle to make it autonomous. Okay. So I'll go back to here. Okay, so this, moving on to software, I'll just say a few words about this open source project called ROS. It stands for Robotic Operating System. For those of you who don't know, ROS is basically a collection of libraries and tools designed to simplify software development and testing for robots. It comes with a lot of process abstraction, hardware drivers, communication protocols, and visualization tools all right out of the box. So our platform uses ROS, and you'll discover that ROS is really popular in the robotics community. So if you're interested in that, I would encourage you to explore it. Okay, so now let's talk about Julia. On a conceptual level, our project spans at least 3 different engineering domains: control theory, robotics, and cloud services. In short, we use Julia to implement optimization-based algorithms to make the vehicle autonomous. More specifically, we use model predictive control, which I'll talk about more shortly. For implementation, we use Julia and JUMP, the Julia for mathematical programming, which Miles talked about yesterday, because it provides a fast, syntactically clean way to construct optimization problems, and we can then feed this problem into an open source solver. We also use a package called Robot OS, which basically provides an interface between Julia and ROS. I should also mention this, that this is not the focus of my talk, but we also have cloud services so that after an experiment, all the data is automatically uploaded to the cloud and is accessible via a public URL for anyone to download. So this is really great if you're working with a bunch of teammates and you run an experiment here, he's processing the data over there. But for the remainder of my time, I'll focus on Julia and optimal control. Again, we use model predictive control. In the video I showed, we used MPC, the same thing. So the basic idea of MPC is to repeatedly solve an optimization problem. And the optimization problem uses a physics model to predict the future of the system, and it optimizes the input according to some goal called the objective function. So here we have like a physics model called the kinematic model to capture the trajectory or the motion of the vehicle. And with this information, the optimization problem propagates the dynamics forward in time and predicts the future position of the vehicle. And then with this information, you can try to optimize the inputs according to that goal you specified in your objective function. And so like for this case, like the 2 inputs, for example, would be the steering angle and the acceleration. And the problem is updated at every time step because you're constantly getting measurements from the environment updating. So that's just a really short intro to MPC. So I understand this is a really brief intro, but here's a code snippet to make some of these ideas more concrete. Again, we start by studying the physics. We need to have a model of the system to predict how this will behave. And then we build our optimization problem. So for this, we use Julia and IPOP. So here what you can probably see is that the expressions on the right look a lot like the mathematics on the left. So this is one of the really powerful things about Julia. Okay, I'm out of time, but if you find this project interesting, we welcome you to visit our website, barkproject.com. Here you'll find documentation on actually how to build this yourself if you want to. Additionally, you'll find a link to our GitHub repository. And so these open source and low-cost initiatives represent an effort to make our research more transparent and accessible for other research groups to duplicate and build on. So I'm done now. I'd like to thank JuliaCon, my professor, Tony, and all of you guys for listening. Thank you.